In this video, we introduce the idea and notations for function compositions. In other words, functions of functions. And then we work a variety of examples, including functions given by formulas, tables, and graphs. And finally, we give some examples of function decomposition. In other words, expressing a complicated function as a composition of two simpler functions. So to start things out, a function composition or function of a function, we'll call it h of x, can be written as g of f of x. In other words, we use the output of the function f of x as the input for the function g. This can also be written in the circle notation as g circle f of x. And these two things mean precisely the same thing. G circle f is just g of f of x. To make it clear what we mean by function composition, we'll work a quick example. So in this example, we're saying f of x is the sine function, sine of x, and g of x is the square root function, just square root of x. In part A, we want to compute h of x, where that's g of f of x. So to get this done, we just replace f of x with its definition. That's the sine function. So I have g of sine of x. And when I replace x with sine of x in that function g, I get the square root of the sine of x. So there's h of x. In part B, we're looking at the composition in the opposite order. So I'm saying this function j of x is f circle g of x, which means precisely the same thing as f of g of x. So that's f of square root x. And when we take that function f and replace its argument with the square root of x, we get sine square root of x. So we can see that taking this composition in different orders results in a different final function. In the first case, the square root of the sine function. In the second case, the sine of the square root of x. Now in part C, we want h of pi over 2. And there's two different ways to do this. We have a general formula for h already because of part A, and we could just evaluate that at pi over 2. So h of pi over 2 is the square root of sine pi over 2. And remember, sine pi over 2 is 1, so I have the square root of 1, and I get 1. Now the other way to do this is to actually just sub in that pi over 2 right from the beginning. So h of pi over 2 is g of f of pi over 2. We're really doing the same thing, just using our specific point from the beginning instead of getting a general formula for h of x. And f of pi over 2, that's the sine of pi over 2, that's 1. So I get g of 1. And then g of x is the square root of x, so g of 1 is the square root of 1. And of course, we get the same answer of 1. In part D, we're asked to get j of 0. And j is this composition taken in the opposite order. That's f of g of x. And again, because we already have a general formula for this, knowing that j of x is the sine of the square root of x, we can just go ahead and use that. And j of 0 is the sine of the square root of 0, which is the sine of 0. And remember, the sine of 0 is 0. Again, if we don't already have a general formula for the composition handy, we can just go ahead and plug in this specific x value from the beginning. So really what we're talking about is f of g of 0. And g of 0, given that g is the square root function, g of 0 is 0. So I end up with f of 0, and that's the sine of 0. And of course, we get the same answer, 0. Now in the next example, we look at two functions that are defined by just a discrete set of points. So f of x is defined by this first table where we have a few x values connected to y values. G of x is defined by the second table where we have a few more x values connected to y values on the function g of x. So in part A, we're asked to compute f of g of 0. And all you have to do here is compute g of 0 first. So when I look in this first table, I see that g of 0 is 3. So what I get out of this is f of 3. And then we just hope that the x value 3 is in the table for f of x. And of course it is. And I see that f of 3 is 2. And we're done with that one. In part B, we want g of f of 2. So we do a similar thing. F of 2 is negative 1. So what we want here is g of negative 1. And then we have to hope that negative 1 is a listed input value in the table for g, and of course it is. And I see that g of negative 1 is 0. So we're done with that one. A third type of problem you might see in a typical calculus book is a graphical definition problem. So we have two functions that are defined by their graphs, And these happen to pass through several integer points on the graph, so we can read off precise values from the graph. So g of x looks like a linear function, and f of x looks like a quadratic function. You don't need to bother getting symbolic formulas for these things, because we're just going to look at a few specific points. In part A, we're asked to compute g of f of 0. So we need to look at the graph and figure out what is f of 0. So f is this yellow curve, the parabola. And when I look at x equals 0, I see that's connected to y equals 3. So f of 0 is 3. So g of f of 0 is g of 3. And then we hope, again, that this turns out to be an integer point on the graph so we can confidently say what the answer is. So when I look at x equals 3, I go to the y value on the function g of x, and that turns out to be 4. So g of f of 0 turns out to be 4. In part B, we want f of g of 2. So this time we start out by finding g of 2. So I go to x equals 2, and the y value there turns out to be 1, 2, 3, 4, 5. So g of 2 is 5. And I want f of that value. So I want f of 5. So if I go to an x value of 1, 2, 3, 4, 5, and I look on the curve of f of x, again, it's passing through an integer point because the problem was set up to work out cleanly. And it turns out that f of 5 is equal to 4. Finally, we're going to look at the reverse process, or function decomposition. And this is actually a really important skill in calculus because this kind of thinking is critical to computing derivatives of function compositions later in the course. So in the first few examples, we're asked to express the given function as a composition of two simpler functions, f of x and g of x. And then in our second example, we're actually going to look at a composition of three functions. So in part A, I have x minus 3 raised to the third power. And so the way I look at this is that I have an inner function, x minus 3. And I'm going to say, let f of x equal x minus 3. Then what I want to do is compose that with the cubing function. So I want to apply the cubing function to f of x. So g of x, we'll call that the outer function, is going to be the cubing function. It takes its input and cubes it, so it's x cubed. And the idea here is that we want g of f of x to represent this original function. And I just want to verify that that works. So g of f of x is g of x minus 3. And when I sub that x minus 3 into this function g cubes that input. So I end up with x minus 3 quantity cubed. So it's working. In the next example, we do a similar type of thinking. We look for the inner function, and I'm going to say f of x is equal to x plus 5. And then our outer function that we apply to that is going to be the square rooting function. So square root of x, it just takes its input and square roots it. And now just to verify, if I compute g of f of x, that's g of x plus 5. But when I sub in x plus 5 to the argument of this function g, the output is the square root of that. So I end up with the square root of x plus 5. So that one's working too. Now in part C, I have 3 times the cosine of pi x. And so the way I'm thinking about expressing this in terms of simpler functions is that the inner function is pi x. Now to get this original function, 3 cosine pi x, g of x must be 3 times the cosine of x. So it's going to take 3 times the cosine of whatever the input is. Now when I compute g of f of x, that's the same as g of pi x. And replacing the argument of my function g with pi x, I get 3 cosine pi x, and we're done with that one. Finally, in the last example, we have this function k of x, 5 tangent of root x plus 3. And we can think of this as a composition of 3 functions. So we could just say it's a composition of 2 functions where the inner function is square root of x plus 3. But we're going to drill deeper than that. And we're going to say the innermost function is actually just square root x. So I'm going to let f of x equal square root of x. Now the function I have to apply to that to get square root of x plus 3 is just the function that adds 3 to its input. So g of x is going to be x plus 3. Just to verify real quick, g of f of x is going to be g of square root x. And when I sub in square root x for the argument of g, I get square root x plus 3. So now we're done expressing the part inside the parentheses as a composition of 2 functions. And the last thing I need to do is wrap this all in an outer function h of x. that gives me 5 times the tangent of that inner function. So h of x is going to be 5 tangent of its input x. Now just to verify that this is all working, we can look at h of g of f of x. And just replacing f of x with square root x, this gives me h of g of square root x. But g of square root x, we already figured this out, is square root x plus 3. So I end up with h of square root x plus 3. And finally, h is the function 5 tangent x. So we take 5 times the tangent of its input, and I get 5 tangent of square root x plus 3. And we've successfully built this complicated function as a composition of 3 simpler functions: the square rooting function, the function that adds 3, and the function that takes 5 times the tangent of the input. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.